Hello, and thank you for joining the session on Lakehouse architecture implementation using Apache HUDI on Amazon EMR and Amazon Redshift. I am Niladri, Specialist Analytics Solution Architect here at Amazon Web Services based in Singapore. Later, I'll be joined by Harsha Shastri, Platform Architect at Halodoc, and Jitendra Shah, Senior Data Engineer at Halodoc, to talk about their architecture, design considerations, and learnings when building a modern data lakehouse on AWS. This is intended to be a 300-level session, so having a basic understanding of data lakes on AWS would be helpful but not mandatory. We have an action-packed agenda. First, we'll quickly set the stage on modern data strategy and what it means for our customers. Then we will look at what were the challenges in traditional data lakes and how it has evolved over the years using current generation frameworks and toolings. There are different data management frameworks like Apache HUDI, Apache Iceberg, Delta Lake, and AWS Lake Formation governed tables, which solves these challenges and are transforming the way data is managed in data lakes. However, today we'll dive deep on Apache HUDI. We also look at how in 4 easy steps you can integrate Apache HUDI with AWS services. Then I'll pass it on to Harsha and Jitendra from Halodoc to talk about their architecture. So let's jump right in. Organizations have data stored in various silos, which leads to inefficiency, scalability, and governance problems. Now, the ability to easily access, combine, prepare, analyze, and perform machine learning with their data in an agile, scalable, secure, and cost-effective way is still cumbersome, time-consuming, and expensive. Taking a one-size-fits-all approach to analytics eventually leads to compromises. We hear from customers that they need the right tool for the right job. Organizations need new data stores that will scale and grow as business needs change from gigabytes to petabytes today and exabytes in the future. A modern data strategy lets organizations break down data silos, empower their teams to run analytics or machine learning using their preferred tool or technique, and manage who has access to data with the proper security and data governance controls. With a modern data strategy, organizations can move any amount of data from various silos into an Amazon S3 data lake and store their data in S3 using standard open data formats to avoid being locked into any one proprietary data format or approach to analytics. Users can then get unified access with the ability to move a portion of their data from one data store to another, and unified governance with the ability to authorize, manage, and audit access to data. Finally, organizations get purpose-built analytics services for their unique analytics use cases. AWS offers the broadest set of purpose-built analytics that seamlessly work with data lakes built on S3, like Amazon Redshift for data warehousing, Amazon EMR for big data analytics, Amazon Kinesis for real-time analytics, Amazon Athena for interactive and federated query across data stores. With modern data strategy approach, organization can use capabilities like AWS Glue Elastic Views to effortlessly move and keep data in sync between the data lake, data warehouse, and purpose-built stores. AWS Lake Formation further provides an easy way to centrally define and manage security, governance, and auditing policies all in one place. Okay, data lakes are great. It helps to collect, store, and analyze data cheaper, faster, with unlimited scale. However, traditionally data lakes had some inherent challenges, especially when dealing with transactional workloads. This mainly revolved around implementing common database-style features on data lakes, such as atomic transactions, row-level mutability, indexes, time travel, etc. Let's look at some architectural patterns to be more specific. The first one is streaming ingest pipeline. You have your source application, which are sending continuous stream of events, for example, telemetry data, into a streaming service like Kafka or Kinesis. Then you have Spark streaming jobs running on EMR as consumers of the Kafka topic or Kinesis streams, then persisting the data into Amazon S3 for analytical consumption. But this architecture exposes a few challenges. For example, lack of atomicity, which essentially means ideally all operations executed during a transaction should be either reflected or none are. It is due to this property of a database that the changes made in an open transaction are not visible to the other database clients during reads unless the transaction is committed. And if there's any failure, all operations should be rolled back. Of course, in a streaming ingest pipeline, you would want to have the capability to perform high throughput ingestion and at the same time deal with small file problems. Traditionally, this meant running separate jobs to run compaction for better read performance. Now, on the read side, you would want to have features which lets you query only the newly written data in a table, sometimes referred to as incremental query. Again, you may want to know how your data looked at a certain point in time in your data lake, referred to as time travel. All of this while running your queries using a variety of frameworks and engines. Another pattern emerges when you are doing change data capture from databases using services like Database Migration Service and ingesting them into the data lake. These are high throughput, row-level DML operations. So, in addition to the previous set of challenges, you now would want to have the ability to perform row-level upserts and deletes and clustering by secondary keys. Another pattern we see emerge due to compliance requirements like GDPR or CCPA, where you want to be able to do row-level updates and deletes as well as support your concurrent writes into your data lake for the regulatory requirements. Traditionally, in order to solve all these challenges, organizations had to build additional jobs, duplicate data sets, leading to a lot of heavy lifting and development efforts and operational overheads. So this is where a data management framework like Apache HUDI comes in and saves the day. Apache HUDI brings core warehouse and database functionality directly to a data lake. On the ingestion side, HUDI provides atomic transactions and concurrency control, efficient upserts and deletes, streaming ingestion services. On the query side, it provides advanced indexes, incremental query, and time travel query capabilities. And most importantly, it is a framework which integrates with most of your big data technology stack like Apache Spark, Flink, Presto, etc. And it keeps your data in common open file formats like Parquet. From a data platform administration side of things, it supports asynchronous data clustering or compaction optimizations, file cleanups, and exposes metrics for all your past transactions. Sounds interesting, right? Let's dive deep a little bit. To use HUDI, we need to understand a couple of important abstractions: HUDI table types and HUDI query types. Let's start with HUDI table type. HUDI table types define how data is indexed and laid out on S3 and how is it exposed to the queries. We have copy on write tables, which stores data using exclusively columnar file formats like Parquet. Now, each commit produces new versions of the base files by performing a synchronous merge during write. As a result, the write amplification, that is, number of bytes written for 1 byte of incoming data, is much higher, whereas read amplification is typically 0. This is much desired property for analytical workloads, which is predominantly read-heavy. Then you have merge on read tables, which stores data using a combination of columnar and row-based file formats like Avro. Now, updates are logged to Delta files and later compacted to produce new versions of columnar files synchronously or asynchronously. Thus, this table type attempts to balance read and write amplification intelligently to provide near real-time data. Okay, now let's understand the query types. First, snapshot queries. These queries see the latest snapshot of the table as of a given commit or compaction action. In case of merge on read tables, it exposes near real-time data by merging the base and delta files of the latest file slice on the fly. For copy on write table, it provides a drop-in replacement for existing Parquet tables while providing upserts, deletes, and other write-side features. Second, you have the incremental queries. These queries only see new data written to the table since a given commit or compaction action. This effectively provides change streams to enable incremental data pipelines. Third kind of table queries are read-optimized queries. These queries see the latest snapshot of table as of a given commit or compaction action. It exposes only the base or columnar files in latest file slices and guarantees the same columnar query performance compared to a non-HUDI columnar table. Okay, now that we understand the core concepts, let's look at the 4 easy steps to integrate HUDI in your pipeline. Let's imagine you are writing a HUDI dataset using Apache Spark. So step 1, each time you write a data frame to a HUDI dataset, you must specify data source write options in the single HUDI options variable. Do take note of the most common options, for example, table name. This is self-explanatory. Then you have record key field, which is a key that uniquely identifies a record. Followed by, you have the partition path field, whose value will be used for partitioning. Then you have the pre-combine field option, which is used when 2 records have the same key value. HUDI picks the one with the largest value for the pre-combined field. Then finally, you have the table type option, which mentions if it's either copy on write or merge on read table. Other options you see are mostly related to registering the HUDI dataset table in your metastore, which could be a self-managed Hive metastore or even Glue data catalog. Step 2, write your Apache Spark data frame. For Spark users, this would be familiar. And additionally, you mention format to be HUDI and include the HUDI options that you have defined in the previous step. Once you write your data frame to S3, if you are using Glue catalog, you should be able to see the tables registered. Notice for merge on read table types, there are 2 tables created. For example, my HUDI table merge on read RO. This is for read optimized view. Then you have my HUDI table merge on read RT for real-time view. Step 3. Now you can perform row-level insert, update, and deletes. You can have your update data frame and mention the write operation to be upserts. It uses the record key, partition path, and pre-combine field to efficiently update the records. Finally, step 4. You can read your dataset using standard Spark options. This could be snapshot query or incremental query. Or you can use standard SQLs to query your data. Apache HUDI is widely supported across different AWS services, such as Amazon Athena, Amazon Redshift Spectrum, for consuming data using standard SQL. You have Amazon EMR and AWS Glue for ETL, and AWS DMS for CDC integration support, and finally AWS Lake Formation for fine-grained access control. With that, I'll pass it over to Harsha Shastri and Jitendra Shah from Halodoc. It's a pleasure to have them with us today to share their experiences in building a transactional data lake using Apache HUDI on EMR and Amazon Redshift.
Thanks, Niladri. Hello, I am Harsha and I work as an architect at Halodoc. Today, I along with my colleague Jitendra will be providing an overview of Halodoc's journey into Lakehouse architecture using Apache HUDI deployed on AWS EMR. Halodoc is the #1 healthcare app in Indonesia with the mission of simplifying healthcare for the millions of Indonesians. Halodoc app provides a wide spectrum of services in the patient's healthcare journey. Users can teleconsult with 20K plus doctors, order medicine from 8K plus pharmacies, book lab tests at home, and book appointment across 2,500 network hospitals. We also work with 15 top insurance companies to provide cashless facilities for both online and offline transactions. Technical architecture of Halodoc comprises of Android, iOS, and web apps as user interfaces backed by microservices in the backend. Entire Halodoc tech stack is hosted on AWS. We use a wide range of AWS services: RDS, EKS, MSK, Elasticache, Lambda, Redshift, S3, Recognition. These are some of the important AWS services that we use. With wide range of healthcare services offered by Halodoc, a variety of data points are stored across individual microservices. There is also data available for third-party SaaS products used for customer activity tracking, marketing campaigns, partnerships, and so forth. As stated by Niladri earlier, making these silos data available under a centralized data store is the primary goal of our data platform. Like most of the startups, our initial data platform consisted of RDS and S3 data sources. We used Apache Airflow as the primary ETL tool and Redshift as the centralized data store. Airflow usage is twofold. It is used to migrate data from sources to Redshift, and it is also used to create materialized views on the Redshift, which are then consumed by BI tools like Looker and Metabase. This architecture served us well during the early years when the growth was stable. But with the onset of COVID pandemic, we started to have inorganic growth in our customer base. This, coupled with emerging data use cases like exploratory data analysis of our ML team, required revamping of the data platform. The challenges of the old platform can be broadly categorized into 3 areas: infra, execution, and governance. With the current generation of RA3 Redshift nodes, we are able to separate storage and compute. But back then, we used previous generation of Redshift nodes, which combined storage and compute. Large volumes of data needed to be stored, even if it is rarely queried, resulting in larger shapes for our Redshift nodes. Airflow, used as the primary ETL tool, was good for orchestration, but for complex data processing, we needed a distributed framework like Spark. On the execution front, the platform lacked automation, and hence a lot of manual effort was spent in configuring the pipelines for new use cases. Data latency was another issue. Finally, the platform also lacked best practices like data governance, cataloging, schema modeling, and quality checks, resulting in challenges related to data discovery and quality. While building the new data platform, we went back to the drawing board and started building the system ground up. We started with the analysis of our data consumers, their data patterns, and their data needs. Parallelly, we also worked with the AWS solution architecture team to understand the tech choices that were available on the AWS. Most of the new platform goals were derived from the challenges of our old platform. For pipeline components, we preferred open source frameworks that are managed by AWS. This gave us the best of both worlds, support of open source community and reliability of AWS. To execute this complex project, we had to overcome two constraints: limited set of resources and ensuring business continuity. We are a small team of 4 to 5 engineers, and they had to work on existing business requirement while building the new platform. To mitigate risk, we followed MVP-based approach. In the first milestone, we prioritized the features that were essential to operationalize the platform. This feature prioritization, along with effective collaboration with the stakeholders, helped us to speed up the execution. Primary tech choices to build our new data platform were data warehouse, data lake, and lakehouse. Data warehouses provide faster access to curated data, good for reporting use cases, but they combine storage and compute, hence not economical for use cases like EDA. Data lakes are good for immutable data and provide separation between storage and compute, but not fare well for mutable data. As explained by Niladri before, Lakehouse architecture provides transactional capabilities to the data lake using technologies like Apache HUDI. Lakehouse architecture supports a wide range of use cases like EDA, BI analytics, etc., and is a good choice for building a scalable and centralized data store. But we already had a lot of BI reports which were powered by Redshift. Migrating all these reports to the Lakehouse architecture in one go was a Herculean task. Hence, to support business continuity, we finalized on a hybrid solution. Lakehouse for all the ad hoc analysis and Redshift for BI reporting. In the short term, BI reports continue to be powered by the Redshift, but gradually most of the use cases will be migrated to Lakehouse. So far, we have seen the groundwork done before building the new data platform 2.0. Now, over to my colleague Jitendra for the implementation details.
Thanks, Harsha, for providing insights on our data engineering journey. I am Jitendra Sir, Senior Data Engineer at Halodoc. I work on building and maintaining the data platform to serve analytical and AI workloads. As Harsha already talked about our solution choices, let me walk through what our new and revamped data platform 2.0 looks like and the components involved. The slide represents overall architecture of data platform 2.0. Here we would like to discuss more on the approach we followed rather than the components involved. On a high level, we have 4 layers: extraction or ingestion layer, processing layer, transformation layer, and reporting layer. We will go deeper into each layer on upcoming slides. The central component of platform 2.0 is a control plane. The idea of having a control plane is to build microservice kind of architecture. It stores metadata and helps easily onboard new tables in the data lake. We have integrated AWS managed airflow service for workflow orchestration. Each component's metrics are logged, monitored, and alerted using CloudWatch and EFK tech stacks. Data governance is always critical for any organization, more in our case since we store healthcare information. We integrated lake formation with data lake to grant and restrict the data access. Great. Let's deep dive on each layer and how it is being designed. The extraction or ingestion layer is responsible for bringing all the source data to the raw zone. Here we mostly leverage AWS data migration service for CDC-based migration. The data source is configurable in the control plane and framework is built to perform the data migration. Each CDC file creation event is tracked on the control plane with the help of AWS Lambda. This helps us to track the status of the file and process it accordingly. Onboarding data with CDC-based approach reduces the data latency for end consumers and perform analytics faster. Processing layer. Here we basically leveraged Apache HUDI and EMR for processing the raw data and maintaining the transactional data lake. All data lake metadata are registered in AWS Glue catalog, which acts as central repository. Data present in the data lake can now be queried through AWS Athena for analytics and also be used through EMR for building the data model on Redshift. The transformation layer is the ETL layer. It consumes data from the process zone on data lake and creates or updates data models on Redshift. This layer makes use of Apache HUDI, Spark, and Hive deployed on AWS EMR for data transformation. All transformations were done based on the facts and dimensions as designed using star schema modeling technique. Adhering to data modeling technique helps us to maintain the warehouse with fewer data silos. The reporting layer is mostly to serve BI workloads. This layer comprises the materialized view and summary table dedicated to reports. Having a summary table reduces lots of processing and improves the performance of Redshift resource utilization. It also helps us to effectively understand the data consumers and their data users pattern. Separating the platform into multiple layers has helped us in multiple ways. Decoupling the processing, granular visibility of the pipeline metadata, and tracking the health status of the components level are some of the advantages we got out of this approach. Great. Till now, we have covered how we designed and architected Platform 2.0 and the implementation strategy. Let's understand further on some of the important principles that we adopted in our data platform journey. Most of our implementation in Platform 1.0 was platform-centric, meaning we manually built pipelines for each data source to serve business use cases. In the new platform, we adopted a framework-driven approach to build components in each of the 4 layers discussed previously. With the framework-driven approach, components are built using configuration data present in the version control system, thereby saving development time. The modular and extendable framework has resulted in a reusable codebase and faster delivery of new features. DataOps combines Agile and DevOps best practices. In Data Platform 2.0, we used ISE, Infrastructure as Code, to provision all our AWS resources. The code changes are deployed using CI/CD. Further, we introduced Liquibase to track, version, and deploy database changes. These best practices helped in reducing manual effort and also associated human errors. The control plane acts as a centralized component that orchestrates pipeline creation and stores metadata about pipeline executions. Control plane uses Python Flash server for exposing the REST API and stores the metadata in MySQL RDS. There are other benefits of integrating control plane in the platform. First benefit, analytics on top of metadata. It helps to understand the current active pipelines, the execution time for job run, understanding the basic transformation applied, and building the data lineage if required. Second benefit, onboarding new tables with a few config additions. Third benefit, we can easily identify the job run status. Fourth benefit, backfilling or rerunning of the jobs can be done by simply updating the state. We talked about how we started our data engineering journey and moved from Data Platform 1.0 to 2.0. The features we implemented and how we are evolving our platform. The outcomes of Platform 2.0 were remarkable and offered significant benefits to us. It reduced a lot of duplicated engineering efforts. It helped to scale our platform with no downtime and serve large-scale analytical workloads. These also enabled faster analytics due to low data latency. We are continuously building, evolving, and integrating new features in our platform. Some of our future work would be on, first, data quality, so that we can provide qualitative and quantitative data to our end consumers. Second, data lineage, to have visibility on a series of transformations that data points have gone through. Third, self-service platform for BI team, to make BI team self-reliant for newer analytics use cases so that DE team can spend more time on platform engineering. Last but not the least, building MLOps platform to support data scientists on EDA and model deployment and tracking. In today's session, we covered Halodoc journey to a new data platform built using Lakehouse architecture on AWS. We also covered our design considerations, best practices, and learnings during the journey. Hope this session is informative, and for more details, please visit our blogs listed here. Handing over to Niladri to conclude today's session.
Thanks, Harsha and Jitendra, for sharing those really helpful insights on the topic. So to wrap up, we looked at some of the challenges in traditional data lake for transactional workloads, then did a deep dive on Apache HUDI, looked at how you can get started and integrate with AWS services. Finally, Halodoc shared their architecture, design considerations, and learnings. Thank you again for attending. We encourage you to get engaged with our training and certification content today to build your skills and get started on AWS. You can also find out more about AWS training and certification by scanning the QR codes on this slide. But before you go, we really appreciate your feedback so that we can better understand the topics and services you would like to know more about. So please do take the time to fill out our survey and let us know what you think. We look forward to engaging with you again at the next AWS event. This is Niladri signing off.